Hello everyone. We are from group of three, from by me, Naya and Rafiu. So today we are going to present one of our CSA project, which is related to a control system in aerospace engineering. So we did a research and finally we decide our topic, which is engine thrust control for turbofan engine. So let us introduce ourselves first. My name is Gan Wee Kyung. My metric number is 217613.
Hi, my name is Naya Naimulhaq, and my matrix number is 213904.
Hello everyone, my name is Rafi Jubair Ahmed and metric number is 213816.
Okay, so without further ado, let us start our presentation of our findings. So I will present my part, which is control strategies. So for the control strategies, we focus on two control strategies, which is PID and another one is mu synthesis. So I will start with the PID first. So PID, also known as proportional integral derivative control. It is one of a very common control strategy used in engine thrust control for the turbofan engine. Its main purpose is to adjust the fuel flow to minimize the difference and the error. So between the desired thrust and the actual thrust produced. So it from the three components. So the first one is proportional terms. So the proportional term is to apply a correction to the magnitude. So the second one is the integral terms. So basically, its function is to eliminate the residue and the steady state error by considering the cumulative error over the time. So for the third terms is derivative terms. So this term is help to predict the future errors by looking at the rate of the change and help dampen the system response to reduce the overshoot. Let's see the function of the PID in the engine thrust control. So this is how it works. First, the sensor will measure or estimate the engine actual thrust. Then the PID controller will calculate how much the fuel need to be injected into the engine based on these three terms. Finally, the fuel system adjusts the fuel flow to match the desired thrust level. So this is how it works. So let us look to another control strategy, which is mu synthesis. So we will focus on dual loop multivariable mu synthesis control. So basically, this strategy control is combined of two concepts. The first one is dual loop control structure, and the second one is mu synthesis. So let us look what is mu synthesis. So basically, it is a robust control technique that focuses on minimizing the worst case gain of the system transfer function, even in presence of uncertainties. So what is the goal of the mu synthesis? It is to design a controller that maintains robust performance and stability by optimizing the mu value to ensuring the system can handle disturbance and uncertainties effectively. So now, what is dual loop control structure? Basically, it contains of two loops, which is inner loop and outer loop, and both these loops has their different function. For the inner loop, it manages fast dynamic and local control. For the outer loop, it addresses lower dynamic and overall system performance. So let us look the application in the turbofan engine. So how does this work in engine thrust control? So for the inner loop, it focuses on controlling the turbine pressure ratio, which is TPR. This is achieved by adjusting the nozzle area, which is directly influence the pressure and temperature of the exhaust gas. So for the outer loop, it controls the fuel flow to achieve the desired thrust, and this loop handles a slower dynamic, like I said just now, to ensure the overall performance meet the required thrust. So for the thrust estimation, which is the third component in this control strategy, a fast and accurate thrust estimation algorithm is used to provide real-time feedback to the control system. So this algorithm is based on the aerodynamic and thermodynamic components characteristic, allowing for their precise estimation of the thrust produced by the engine. So let pass to the Rafael to explain the next part. Thank you.
Next slide, please. Thank you, Jerry. Now I'm going to go talk about the key components in thrust control. First, I will talk about the actuator. The actuator is a critical component in the thrust control system of a turbofan engine. I think at its core, the actuator is often a throttle valve or works as a fuel flow regulator that accurately regulates the quality of the gasoline entering the combustion chamber. In contemporary turbofan engine, the actuator is a vital feature of sophisticated control system such as full authority digital engine control FEDEC, which which considerably decrease the pilot's burden, letting them to focus on the other activities while the systems automatically adjust the engine settings for maximum performance. And next is sensors. For the sensors, we have by three sensors: pressure sensors, temperatures, and RPM sensors. For pressure sensors, these sensors monitor intake and exhaust pressures, helping regulate turbine pressure ratio. And for the temperature sensors, they measure turbine inlet temperature and also exhaust temperature to prevent from overheating the engines. And RPM sensors, they track the rotational speed of low pressure and high pressure rotors to maintain the airflow. Next slide, please. And now we are going to talk about the role of the thrust estimation algorithms. For every other sensors and actuators, we use the thrust estimation. This mainly algorithms use data from pressure, temperature, and RPM sensors to estimate thrust in real time and provide accurate thrust data even when thrust sensors are impractical. And importance for this one is thrust estimation is essential for systems like FEDEC, where real-time data is used to maintain performance, and virtual thrust sensors help improve engine reliability and performance without the need for direct thrust measurement. Next one. Now, control frameworks between FEDEC and dual loop synthesis, mu synthesis, as Jerry mentioned. For the FEDEC, it automates fuel flow, air intake, exhaust, and other parameters to optimize engine performance, reduces pilot overload by ensuring real-time adjustment for optimal engine operation. And dual loop mu synthesis control is a sophisticated control method that adjusts both fuel flow and nozzle area, optimize engine performance, and also handles the complex non-linear engine dynamics by decoding the loops by loops with the help of the thrust estimation. Next one, please. This one is the system integration and performance benefits. I think we have already got a idea for our integration of the component. The actuator adjusts the fuel flow based on the feedback from pressure, temperature, and the RPM sensors. And thrust estimation algorithms calculate the real-time thrust, enabling precise controls. The system works together to provide seamless performance across verifying flight condition, ensuring the efficiency and stability. For the key benefits of these systems, it enhanced engine stability, improve the fuel efficiency, safety and reliability, like protection from the thermal overload, mechanical failures, and other operational risks, and adaptive response. The system adapted to changing flight condition automatically without pilot permissions. My part is done here. I think I will hand over to Naimon.
Okay, assalamu alaikum, and thanks for giving me a chance to speak here. So I will talk about the flowchart of the block diagram. My friend Rafi already talked about the actuators and the sensors already. So how the components work in the aircraft. So a block diagram illustrating this control process would consist of the following elements. The first one is pilot input. Input providing the throttle position sets the target of the thrust level, and the controller, the electronic controller, is a FADEC. That's also called full authority to. That is the that components act as the brain of the aircraft that process the pilot's command and comparing them to feedback from the sensor, and the sensor monitor the parameters such as spool speed, exhaust gas temperature, and the ambient condition. And then the actuator includes fuel flow regulators, guide vane actuator, and the exhaust nozzle mechanism that execute the FADC commands. Turbofan engine. physical system producing the thrust, and then feedback loop include the sensors between the desires and actual thrust are corrected in the real time. In the next slide. So the mechanism of the flow chart is pilot input the required thrust in the throttle, and then the FADC, the controller, which also the full form is the full authority digital electronic controller, receives the signal from the pilot, the throttle, and then it converts the electronic signal to the mechanical signal. Next slide. So actuator converts the signals to mechanical movement, and it provides to the turbofan. We can see some parts in the left side also. So can you move to the next slide also? So an aircraft engine sensors are also called feedback sensor. So there are 7 types of feedback sensor here. I'm sorry because my laptop is not working, so I have to use my friend laptop. Agent. So there are 7 types of sensors in the turbofan engine. So FADC pressure controls sensor, and total air temperature sensors, and high temperature pressure sensor, and RTD temperature sensors, and thermocouple speed and RPM sensors. There are many types of sensors there. Can you move to the next slide? দেখা যেতে পারতেছি না আসছে then FADC process the FADC. Oh, sorry. The sensors sends the commands to the FADC again if the signals given for the thrust is required at the moment. That's all from me actually. Thank you.
So this is all our findings, and thank you for listening.
I messed up.